Hi, I'm Paul. We are doing Leetcode must-know interview questions, and today's challenge is clone graph. So we're in the middle of the graph section of the must-know interview questions. I think all of the graph questions actually are rated medium. This one is rated medium. Given a reference of a node in a connected undirected graph, period, return a deep copy clone of the graph, period. There's nothing wrong with the grammar there, but I don't know. A connected graph means that there's a path between any pair of vertices in the graph. I mean, maybe not a direct path, but you can get there. There isn't any isolated node or subgraph sitting off all by itself. All right, each node in the graph contains a value, which is an int, and a list of its neighbors. Test case format. For simplicity, each node's value is the same as the node's index, one indexed. For example, the first node with value equals 1. The second node value equals 2, so on. The graph is represented in the test case using an adjacency list. Okay, that's not important. In the test case, yeah, it just looks funny in the test cases. You know, here's the input, the output, but that's not really what we're going to get here. We're just going to get a node passed in. Adjacency list, yeah, that's one way of representing graphs. So for you basically have an array. Each cell representing a node in the graph, and each one has a pointer to the other nodes that are adjacent to the node in question, which is what we have here. We've got nodes, it has a value, and it has a list of adjacent nodes. All right. The given node will always be the first node with value equals 1. You must return a copy of the given node as a reference to the cloned graph. All right. I'm trying to see how much room I have here. I don't really have as much room as I would like in order to sort of sketch something out. But let's talk about how we would do this using the example that they have here, where it says original graph, 1, 2, 3, 4. So we can traverse the graph. We can do a depth first search. We need, though, to, we can traverse the graph, and as we hit each node, we create a clone of the node. The problem is that the graph may have cycles, may have shared neighbors. This graph here, for example, has a cycle. So we don't want to just go on forever. I mean, we could go to 1, 2, 3, 4, 1, 2, 3, go back around. So we have to have some way to know that we've already visited a node. And we can do that with a hash map. So let's say we start with node 1 and we clone it, and then in the hash map we put the original node as the key and the cloned node as the value. All right, then we go to the neighbors 2 and 4. So for 2, we're going to do the same thing. We are going to clone it, put it in the hash map, and then deal with its neighbors, which are 1 and 3. But we can look at the hash map and see that 1 has already been cloned, so we're not going to clone it again. We're just going to add the clone as a neighbor to the clone of 2. So that's the idea. We have a hash map to avoid infinite loops. Make sure that neighbors are not duplicated in the new graph, and that should give us what we need. All right, I'm going to pull this over here and see if I can kind of simulate what we're going to do. So the problem says it's going to pass in node 1 first. So we get node 1. We're going to clone node 1. Actually, let me label this. This will be our hash map. We'll have keys and we will have values. And over here, we will have neighbors. So key is 1. Value is a cloned node. Wow, that was weird. A cloned node of 1. All right. Now, for each neighbor of 1, we're going to add a cloned. We're going to add a cloned version of the neighbor. How did that happen? All right, so the neighbors are 2 and 4. Okay, so the first thing we want to do is we want to add a cloned version of the neighbor 2. So we're calling this recursively. All right, we were calling the same method now that we called on node 1, but we're calling it on node 2. So what we're going to do is we are going to add node 2, and we're going to add a cloned version of node 2. And then for the neighbors, we are going to add cloned versions of the neighbors. What are the neighbors of 2? I didn't mean to do that. What are the neighbors of 2? Well, it's 1 and 3. So the first thing we do is look in the map and we see, well, 1 has already been cloned. So as a neighbor, we can add the cloned version of 1. 3 is the other neighbor, all right? So we are going to do this recursive call again on 3. 3, we're going to clone it and put it in the map, okay? And now we are going to add cloned neighbors of node 3. The neighbors of node 3 are 2 and 4. If we look in the map, we can see that 2 is already cloned. So we can just add 2, right? We also want to add 4. 4 has not been cloned yet, so we're going to create a clone of 4 and put it in the map, right? We are going to do a recursive call on 4. The neighbors of 4 are 1 and 3. Those have already been cloned. So we can just add clone 1 and clone 3 to the neighbor list of 4. All right, now we're starting to unwind the recursion here. So now we can add the cloned node of 4 to 3. Okay. We can add the cloned node of 3 to the neighbor of 2. And we can add the cloned nodes of 2 and 4 to 1. Okay? And that should give us the answer that we want. So let's see what an implementation would look like here. So actually, you can see what we got here. What the way they list the answers is, the answer for this is neighbor list 2413 2413. I'm going to exit that in order to scroll, but you can see the output here. That's what they want. 2413, 2413, but they're clones. Okay, let's move this back over so we can write some code in here. Okay. First thing we need is we need a class. We need a class property, and that is going to be our hash map. So a private, and that doesn't need to be capitalized. Private map. The map is going to be node to node. Let's call it visited, so we know which nodes have already been visited, and that will be a new. I'm gonna need more room here. Scoot this over. A new. Let me move this down a little bit. Maybe we need to look at that, but it's going to be a new hash map. Oops, you see, that's not where I wanted that. Okay, I want that actually up here as a class variable. All right, public node clone graph. Well, it's possible. I'm looking at the constraints here. Number of nodes in the graph. Number of nodes in the graph is in the range of 0 to 100. So it's possible that we get just an empty, that we get a null pointer as the input. No repeated edges, no self loops, connected. I think we went over all this. Okay. But we do have to handle this edge case, which is that the input could be null. Does it say what to return for that? I assume we just return null. Oh, here it is. Okay. So there's an example here. Example 3. Adjacent list, for our purposes, that is null. And the output is null. I guess we could just return node, would be the same thing. All right. What's next? If we need to know if the node that was passed in has already been visited. In other words, have we already cloned it? So if visited dot contains key node, then return visited dot get node. Return the cloned node. Return the cloned node if it's already been cloned. All right. If it hasn't been cloned, let's clone it. We'll create clone node equals a new node with the same value. And put it in the hash map. Visited dot put node clone node. All right. Clone it, and we put it in the hash map so that we know that this node has already been cloned. All right. Now we got to deal with the neighbors. The neighbors of the node. So for we can do a for each loop here for node neighbor in node dot neighbors, which is a list, right? It's an array list. Yeah, it's an array list. for each neighbor in the neighbors list, we are going to add to the cloned node, to the neighbors list, I should say, of the cloned node, we are going to add, we're going to do a recursive call here, we're going to add a clone of the neighbor. Now, it's possible that the neighbor's already been cloned. In that case, I mean, what's going to happen is we'll do clone node, neighbors add, and then call clone graph on the neighbors. So for example, when we did that like on node 2, the neighbors are 1 and 3. So we are going to do this. We are going to add to the cloned 2 node, to the neighbors list of the cloned 2 node, a clone of node 1. When we call clone graph on node 1, it's going to come down here and say, no, we already cloned it. So it's just going to return the clone, and we can add the clone to the list. If the clone is not in the list, we will clone it. And we will proceed from there with the neighbors of that node. All right. And I think that's all we need. The rest of it is just recursion, which is going to traverse all of the nodes, all of the neighbors. And so after that, we can return clone node. All the recursion has unwound, and we're back at node 1, or a cloned version of node 1. And we're going to return it. So let's try it. Accepted. I like it when it works the first time. Okay. Let's try the full submit. All right. 25 milliseconds. Oh my gosh. All right. Well, we're kind of somewhere in the middle there. That's the runtime. Runtime. I'm sorry, that's not true. We're actually a little bit ahead of the curve here. 72 memory. Okay, what's the complexity of this? We visit each node, so that's O of n, but then it also depends on how many edges we have. If you put more edges in there, it's going to take longer. So really, it's nodes plus edges. So like n plus e, or whatever variable you want to use for edges. Let's take a look. Oh, v plus e. Okay, vertices plus edges. Okay, fair enough. Memory is just well, we need to store cloned nodes, so it's just O of n, right? Or O of v. Okay. All right, that's our solution for clone graph. I hope you enjoyed it. Please feel free to subscribe, like, comment, and see you next time.